It's a pleasure to introduce George Tynan, who I think most of you know, but if I remember his history, he started out in aeronautical engineering, I believe Cal Poly San Luis Obispo.
Yep.
And he did his PhD at UCLA. It was never clear to me who his advisor was, but I do know his name was Bob. And there were a few possibilities. And after that, he was in the real world for a while before he went recidivist and returned to academia. And he's held a variety of positions like Associate Vice Chancellor for Research and Associate Dean for International Affairs, which boosted his frequent flyer mileage, and now Chair of Mechanical Engineering. So I'm waiting for the day when he has to do a real job and look like the working stiffs like the rest of us. And
the computer seems to have locked up.
And it can keep going for a while. And in between all this, he has worked on turbulence in both tubes and tokamaks and the LH transition, and also worked on plasma material interaction and made important contributions in all of them. So now that you've been switched on, off you go.
The computer is still there. You should carry on. The computer is still there.
So thank you, Pat. And it's my pleasure to be at another X Festival. Can everyone hear me okay? I presume in the back of the room. Oscar, online is okay?
Yes.
All right. So this is going to be a whirlwind tour of going from very quickly over some results from a basic laboratory plasma experiment that, particularly for those of you who are perhaps new to this game, might help provide some context, and then we'll pivot and spend most of the time looking at tokamak results. There's basically 6 main points from the fundamental or basic experiments. I'll just literally spend about 3 minutes on this and then jump to the tokamak. You can, in controlled experiments, you can actually follow the development of turbulence from a quiescent plasma state to a coherent eigenmode. You can watch that coherent eigenmode develop several different branches. They begin to interact non-linearly. You get a mode lock state. As your control parameter increases further, you can then eventually see a transition to a state of weak turbulence. I use the phrase weak turbulence because the underlying fluctuations still more or less follow the linear dispersion relation, but they have a broad frequency and wave number distribution. You also get eddy tilting, anisotropic turbulent eddies form in the plasma, and those eddies begin to get an elliptical shape. They tilt, and that then begins to transport angular. Hey, Lothar. They begin to transport azimuth momentum radially, so that gives you a finite Reynolds stress. As the turbulence goes from a coherent state to a turbulent state, we also get the onset of a turbulent-driven shear flow, which has the characteristics of what theorists, which you guys refer to as zone flow. It's really a result of very small scale, centimeter scale vortices merging into a system scale shear flow. So in the language of, in the Fourier domain, you would say this is a non-local transfer from high wave number structures to very low wave number k theta 0 structures. This can lead to predator-prey like dynamics, where you go to an oscillation state between high turbulence and weak shear flow, and then the turbulence energy gets coupled to the shear flow is amplified, turbulence energy drops, and then the state so sits there and oscillates back and forth. You can also get depending on how you tweak the parameters, you can also get a steady state experiment condition as well. And just as an aside, much to my surprise, Pat had predicted this, argued that it should happen, and I was very skeptical, but the turbulence can also drive parallel shear flows as well. So let me just give you a quick summary of what that looks like. This is a sort of a computer rendering of the device. It's about 3 meters long, makes a plasma. Just imagine a cylinder of plasma about 10 centimeters in diameter, about 3 meters long, immersed in a solenoidal magnetic field. You can stick Langmuir probes in it to your heart's content because it's low temperature. You can use high-speed imaging to look along the end to actually watch the structures develop. This is the dimensionless parameters that we operate in if you're curious. As you rate the control parameter, and what I'm going to show you today is the magnetic field. So you just increase the magnetization of the ions. As you do so, at fixed RF power input, the plasma density begins to climb, as does the electron temperature. That means the pressure gradient increases. Pressure gradients drive drift wave instabilities. You can go calculate from linear theory the real and imaginary frequencies. And so you see for conditions of this case, we had 3 azimuthal eigenmodes that are unstable, that positive growth rate. And as you crank up the magnetic field, more and more modes go unstable and they start to interact non-linearly. And so as you follow the fluctuation amplitude, at low field is essentially 0. Fluctuations turn on in a critical field. They rise in magnitude to some value. Here's a profile of the density fluctuations. Essentially, here's the mean profile. And then you can see the fluctuations on top of it, and you see the fluctuations concentrated in the region of sort of the background gradient. That's because they're driven by the pressure gradient. And so this is the mean density, is fluctuating density profile in a coherent eigenstate. You can calculate eigenmodes to your heart's content, and they sort of look like what you see in the experiment. As you raise the magnetic field, the wave steepens. There's a pretty easy way to understand that, but we'll discuss that in the Q&A if you're curious. And if you look at it in the configuration space, this is the light intensity. Total light intensity is a function of time, with about 3 microsecond time resolution between frames. If you subtract the time average intensity from it to get a fluctuating intensity, then you see essentially the density fluctuations in the lower frame. And here it's basically an n equals 1, n equals 2 sort of states that are sort of interacting. And as you look farther over, you get much more complex behavior. And if you stare at this long enough, you can see that there's actually sort of a shear layer about halfway out in the plasma. And that's the development of the turbulent driven shear flow. The spectra in the Fourier domain, spectra just get broad. Skip that, skip that. If you integrate over frequency and just plot a wave number spectrum of the total energy of the fluctuations, what you see as you go from, this is sort of a mode lock state with several different large amplitude eigenmodes. As you raise the field further, you get a broadband spectrum. And the really interesting thing is the low K part of the spectrum, which is linearly stable. The energy in that part of the spectrum increases by 2 to 3 orders of magnitude as you go into the turbulent state. And as that low K part of the spectrum fills in, you also observe the onset of the shear layer. This is the radial profile on the horizontal axis, and this is the azimuthal ion velocity measured using laser-induced fluorescence. So LIF actually measures the distribution function of the ions, and you can actually see it offset from 0, showing the onset of an azimuthal flow. And then at critical magnetic field, you actually get this shear layer that develops at the edge of the plasma. So the Reynolds stress, if you guys are all familiar with this, the Reynolds stress is a correlation between 2 fluctuating velocity components. And so you get a Reynolds force from the divergence of the VR between the stress. You can calculate the rate of work done by the turbulence on the shear flow by multiplying this Reynolds force by the fluid velocity. And in the steady state, at least, that has to be balanced by the rate of dissipation of the energy in the shear flow. So when we saw evidence that the shear flow was actually developing, we then developed a Langmuir probe array to measure the stress. And in fact, you get a finite Reynolds stress. If you then plug that measured Reynolds stress into a momentum balance analysis, you'll get, let's see, the black solid line is what you get from momentum balance. Our measurements, probe measurements of the flow velocity is sort of black diamonds. I'm sorry, that's the fluctuation velocity profile. The green is the measured fluid velocity profile. And then up here, I'm showing you three different PDFs of the velocity fluctuations. The radial velocity on the horizontal axis, the azimuthal velocity on the vertical axis. And you see that these PDFs are tilted. And as you move across the shear layer, the sign of the tilt changes. And that is indicative of the existence of tilted turbulent eddies and a finite stress. As you raise the field a bit further, something interesting can happen. The plasma can jump from a state of higher amplitude fluctuations. This is potential fluctuations in the top, density fluctuations in the bottom. As you raise the field from about 1100 Gauss to 1300 Gauss, you see a drop in the amplitude of the fluctuations, and that corresponds to an increase in the shearing rate of the E cross B flow. This is normalized to the turbulent correlation time. And so the simple picture of shear flow decorrelation of turbulence, drift turbulence, suggests that when this value exceeds about unity, that the shear flow should be effective in sort of suppressing or at least reducing the turbulent fluctuation amplitude. So at least qualitatively, it looks kind of like that expectation. And then the interesting thing is that that has an effect on the radial profiles. So when you have high amplitude turbulence, here's the density profile on top, and bottom is ion pressure profile. And then once the turbulence gets quenched, or it doesn't go to zero, it's a smaller amplitude turbulence, you get a steeper profile. And so that's the sort of the feedback effect of the turbulence on the equilibrium of the plasma. Yeah.
The previous one, in the simple, yeah, here where you have the blue arrow, you actually have zero or very low. Yet you have a very strong reduction of the fluctuation.
Yeah, you have to keep in mind this whole system is, I mean, we're used to thinking of plasmas that are very long relative to the scale of the shear flow and the turbulent structures. In this experiment, they're all comparable scale. So there's no real scale separation. It's one of the disadvantages of such experiments. So anyway, so the basic experiment shows a bunch of signatures that we're going to now see when we go to the tokamak case, looking at the development of the turbulence from the underlying instability, seeing the development of anisotropic turbulent structures, development of the finite stress, turbulent stress, or Reynolds stress. That Reynolds stress can amplify. I didn't go into it too much detail, but there's a very weak background shear flow, even without fluctuations. And so my interpretation is the stress sort of amplifies that equilibrium shear flow. And the phenomena is really due to the merger of small scale structures at high K, if you want to think in Fourier domain, into a K theta of 0 shear flow. And I haven't discussed it because of lack of time, but you can also see the onset of radially sheared parallel flows as well, driven by turbulent stress. So that is the sort of background to sort of normalize everybody. What are we, 13 minutes in? So I would like to now present a couple of results here. The LH transition, I think many of you are familiar with, so I'll probably jump through this pretty quickly. But I'd like to show some evidence in tokamaks that these phenomenology, these turbulent shear flow interactions, play a significant role in both the core plasma and at the edge boundary. And they also, I think, play a role in the density limit. So the first thing is, first result is just that paper came out last year. It was a collaboration with our colleagues at SWIP, and also Wenbin Liu, who was a student at Tsinghua University. So we used the HL2A tokamak at SWIP. So this is a cross section of the plasma, the axis symmetries on the left, It's a circular plasma with a single null lower diverter. And colleagues from the University of Wisconsin have built a beam emission spectroscopy diagnostic on this device. I'm not going to go into how BES works. Suffice to say that it allows us to make spatially localized density fluctuation measurements with the spatial resolution of about a centimeter or so. And we configured the array, the BES optical array, to look along a minor radius, a chord of the plasma from the edge into about about 1/3 of the minor radius, something like that. And we had every centimeter, we had a data point going in radially. And we had two arrays that are separated colloidally at each radial position. So it's basically a 2x16 array. This allows us to infer the radial profile of density fluctuations of the laboratory frame fluctuation propagation speed and so on. So what I'm showing here is an example of what you can get from analysis of the data. You take 2 points here. Imagine the plasma is flowing, say, upwards. There'll be a slight time delay as the density structure goes from this point to this point. You can measure the phase shift from that. And from that phase shift, you can estimate the wave number that that structure must have had. And you see thousands or even millions of these events go past you. You can build up a histogram of their frequency and wave number, essentially the dispersion relation of those fluctuations. So that's at one time slice, that's such a frequency wave number spectrum. You can get a variety of other measurements as well. The dispersion relation, you can measure the radial correlation length as a function of radius. And so what you'll see is it's sort of modulated. There's regions where it's small and then regions where it gets a bit larger. And then you can also build a time space map of the density fluctuations. So this is time here. This is showing, this is 100 microseconds of time. So this total time duration here is about half a millisecond or so, going from 182 centimeters to out here 200 centimeters. And the plasma elastic flux surface is somewhere about here. So what you notice is these radially elongated structures that are alternating in color, which means positive and negative density fluctuations relative to the mean. And there's also, if you stare at it, there's like places where it looks like the structures have a difficult, these radial extended fingers have a hard time penetrating. And there's like several of those locations. So to measure the profiles of the density and electron temperature, this is using fast swept reflectometry, and then also high resolution ECE emission. You look at the profile, there's like these little wiggles on them. They're just very subtle. And I'm showing you the estimated gradient of the electron temperature and electron density. There's like these small modulations in the density in the gradient, the scale length. And we've labeled them as these 3 different positions. If you just had this by yourself and say, well, I'm not really sure, it's about on the edge of the uncertainty of the error bars. Down here, I'm showing the radial correlation length of the turbulent structures, and that has some weak modulation on it as well. And then the calculated Q profile is shown down below. So point number 1 is there's some hint that there's some corrugations in the time average profiles. Point number 2 is if you sort of zoom in on the time space plot of the density fluctuations. This is sort of a little bit of a zoom in. And again, you could, the locations of those correlations from the previous slide are shown by the 3 asterisks here. So this outermost one is the last close flux surface. And there seems to be a couple other locations where we had correlation, the corrugations. And if you look at these inward and outward going events, I guess I should say, some of them have a slope going from the lower left to the upper right, sort of a slightly slope like this. That's an outward going event. And occasionally there's something that looks like this, which is an inward going event. And if you stare at them, sometimes you can convince yourself it looks like they stop at different locations. Clearly at the last close slug surface they stop, but at about this location, maybe further in, I'm not sure. They seem to encounter some mechanism that's stopping them from propagating. So that's point number 2. Point number 3 is if you look at the colloidal flows at the different radial locations, you see reversals in the propagation direction. So going from this region to this region, there's a clear flip in the wave number sign, which is a manifestation of fluctuation that's propagating in the different direction colloidally. And then you go a little bit further out, you see another such propagation flip. And then at the last close flux surface, you see another one like that. And these arrows and these red lines are showing you where the corrugations were in the first profile plot that I showed you. And then finally, if you look at the cross correlation between structures, between data points radially separated and separated in time, which is sort of a proxy for eddy tilting, you can see flips in the sort of isotropy or anisotropy of the structures. And then when Bin came up with a little statistic, we wanted to see, could we quantify this sort of barrier feature that seems to be present in the raw data. And so we decided to calculate basically the cross correlation between 2 radially displaced probes, 1 centimeter apart, with 0 time delay, conditionally averaged subject to the amplitude of the event. So sigma is the mean squared deviation of the fluctuation intensity, and then the ensemble average of that is like the average intensity at that given location. And what we find, so that that correlation is what we call the coherence on this vertical axis. And then we can keep track of this value of this coherence for various small and large amplitude events. And that normalized amplitude is on the horizontal axis. And so a small amplitude event would have an amplitude, let's say, less than 1 of the 1 sigma. So that'd be sort of down here. A large amplitude event would be over here. And what you see is, and then we also label the locations where the flow reversals and the corrugations occur by these red asterisks. And what you see is that in between those corrugations, this thing is almost unity. That is, you get long-range structures, long-range coherence. And then at about the location where you have the flow reversals and the corrugations, small amplitude events have a much smaller coherence. That is, they're having trouble passing through a particular location. And large amplitude events have a higher coherency, like they're able to sort of punch through some sort of barrier. And we think that this is a pretty clear indication of E-Crosby staircase behavior. At least it was consistent with what our understandings of that picture would be. So the summary of the results from those experiments is we can see a pretty clear indication of a radial shear and the colloidal propagation of density fluctuations that occurs at least at 3 locations and maybe 4 in the machine. These are, I should say, pretty weakly heated L-mode discharges, about 400 megawatt or 400 kilowatt neutral beam heated discharges, so far away from the H-load threshold. There's some evidence that there's corrugations in the profiles at the same locations of these shear flow reversals. Some evidence for eddy tilting, and the tilting changes across these layers. The radial correlation length is modulated with these structures. And in between these layers, there are these radially extended features. I should say that the propagation distance is 4 or 5 centimeters. The correlation length of a fluctuation is about 1 centimeter. So it's the picture that I have is a small centimeter-ish scale structure that's moving inward or outward radially by 4 or 5 correlation lengths. And then it hits something and stops. Let's see. And these small amplitude events are more effectively stopped at these barriers than large amplitude events. So that is the fairly new result from studies of staircase. How am I doing on time? I think I will, in the interest of time, I will skip forward through LH transition, and then if there's interest, I'll come back to it. Because I'd like to really discuss density limit physics. All right, almost there. So just a minute or so summary of the LH transition results, which are somewhat out in the literature now, so they're not particularly new. And I think Lothar, you're going to talk some about transport barriers next week. There's significant evidence that the turbulent Reynolds stress plays a role. It's probably not the only thing operating, but it plays a role in quenching the turbulence at the last close flux surface in the tokamak device. That momentary quenching of the turbulence by the same basic picture that I showed from the laboratory scale experiment, where the turbulence is dumping all of its energy into the shear flow, and then as a result, the turbulence energy collapses. That collapse in turbulence energy reduces the turbulent mixing at the edge of the plasma. That allows the pressure gradients to build, particularly the ion pressure gradient to build. And the ion pressure gradient can then sustain a sheared radioelectric field independent of the turbulent stress. And so the way I look at it is the turbulent stress acts as to sort of kick the system over the edge once the system gets close to the threshold. But we can discuss that more in the Q&A if you're curious. I'd also like to show some results that I believe show pretty clearly that the same physics, turbulent shear flow interactions, are at play in initiating the density limit. If you're not a tokamak aficionado, if you're running actually, I think other fusion devices also, like accelerators, have density limits as well. So it's not just limited to tokamaks. As you increase the rate of neutral gas injection into the plasma and you raise the density, at some point, you'll see a maximum allowable density. The plasma simply won't take any more neutral gas and turn it into plasma. And what happens is the edge of the plasma cools down. In a tokamak, if the plasma cools down, the plasma gets more resistive. The higher resistivity then changes the current profile in the plasma. The current profile in the tokamak plasma plays a key role in the large scale MHD stability of the plasma. And eventually you can actually trigger an MHD instability and the plasma will disrupt, it'll collapse. And so the density limit is a truly important phenomenological operational limit. It has generally, I think historically, been attributed to purely radiative effects alone. That is, as I put more neutral gas in, the plasma is radiating as it's trying to ionize that gas. A lot of the plasma heat is lost by radiation to the walls, and that's what cools the plasma down. But there were some classic experiments done in the early 80s that showed, by Martin Greenwald, showed that when you inject if you fuel not at the edge of the plasma, but you inject a frozen pellet of fuel into the core of the plasma, so that now the fueling is in the center, not at the edge, that you can greatly exceed, by multiples, the so-called quote unquote density limit. And then the plasma will very nicely then relax back to its unperturbed state, and you don't get a disruption. And that sort of hints that, and Greenwald mentions this in his papers back in the day, says that this suggests that something at the edge of the plasma is at play in setting the conventional density limit. So actually motivated by, Martin came to UCSD about, 8, 9 years ago, gave a seminar on all this stuff. And that got me thinking about, could we do an experiment to test this idea? that maybe something else besides this radiation is at play. And so did an experiment on the HL2A tokamak again in SWIP, and where this is just a purely ohmically heated discharge, so no neutral beams. That allows us to use Langmuir probes, so we can. We're like cavemen, like poking objects we don't understand with a stick, and we can study the same physics: the edge turbulence, the shear flow, the Reynolds stress, the Reynolds work, the exchange of work between the turbulence and the shear flow, and so on, and see how does that evolve as we approach the density limit. So, just in a series of discharges, we gradually increase the rate of gas fueling, keeping everything else constant: magnetic field, shape, plasma current, all constant. And then all the data that I'm going to show you are plotted in terms of the normalized line average density. So N sub G stands for the Greenwald limit, after the guy who discovered it empirically. So the red data points are at about 30% of the density limit. Blue is at about 60, and green is about 80%, basically right on the margin of the plasma disruption. On the top curve is the mean density as a function of radius, and I plotted this relative to the radius of the last close flux surface. So the middle of these plots corresponds to the edge of the plasma. On the right of that is the open field line scrape-off layer region. On the left of it is the beginning of the core plasma. So not unexpectedly, the density begins to increase as we increase fueling. The electron temperature is beginning to decrease. And the electron pressure, simply the product of these two, is increasing slightly, or actually significantly, as we raise the density. And then finally, there's a radioelectric field that exists at the plasma edge. This is a time average. You could think of this as like a steady state radioelectric field. On the open field line region, it's positive. That's what you expect from the fact that the open magnetic field lines are terminating on conducting end plates. And plasma sheath theory says that the potential drop in the sheath is proportional to the local electron temperature. The electron temperature is increasing as you go inwards. And so therefore, the plasma potential should get more positive as you move in from the wall. And that gives you an outward radioelectric field. That's exactly what you see. And then inside the last close flux surface, the radioelectric field is set by a balance between the radial ion pressure and the Lorentz force, the B cross B force from the ions. And what we see is that radioelectric field, it's negative, which again is what you expect from the equilibrium. And its maximum value is shifting a little bit outward towards the edge of the plasma as we raise the density. And its maximum negative peak or peak value is getting slightly smaller by about 30–40% or so. So the slope of that is also evolving a little bit. Yeah. There's no neutral beam injection here, so but we don't have any flow measurements, unfortunately. Either from yeah. Tens of kilometers. Yeah, but also if you go from the linear ohmic confinement to saturated ohmic confinement, it can change. Yeah, but this is more. That's more in the core region. This is the last 2 centimeters, 1 centimeter of the plasma. So, but bottom line is there's no data, unfortunately. Well, the pressure here is the electron pressure, so not the ion pressure. Yeah, and the heating is all going into the electrons because it's ohmic heated. Yes, at least that's what I would think. I would guess, but certainly is something that needs to be looked at. Unfortunately, we couldn't. So, if you calculate the E cross B velocity from the data before, that's what's shown up here. The turbulent Reynolds stress The VR V theta correlation is shown down below in the middle plot. And so you see that this is stress, not the gradient of the stress. And so you see that the peak values of stress are getting smaller as we raise the density, as you go from the red to the green. And slope is decreasing a bit as well. And so if you then work out the Reynolds power, which is the divergence of the stress and multiplied by the velocity with the minus sign to keep our sign conventions correct. So a positive value for this Reynolds power means the turbulence is dumping energy into the shear flow. And negative means vice versa. The turbulence is giving energy, the turbulence is receiving energy from the shear flow. And so what you see again is about a factor of 40–50% reduction in the peak value. This is a positive value just inside the last close flux surface, essentially zero in the scrape-off layer. And then it sort of bounces around a bit and then settles down to something close to zero as we go into the maximum distance we can surface probe. So there seems to be a, let me move, how do I move that up? I just noticed that this thing is right in the way of, there we go. So the rate of the Reynolds work or the shear flow production rate is beginning to decrease as we raise the density. Uh-oh. No, I just broke it. Did it advance? Okay. If you, again, you can play the game where you plot the PDF, the probability distribution function of the VR V theta fluctuations to get a sense of the isotropy or anisotropy of the turbulent eddies. So as you raise the density, you go from a very clearly anisotropic structure to something that's it's still a little bit anisotropic, but it's almost a set of like bullseyes, a circle, and that is an indication that the turbulent stress is going to be reduced as a result of that. So if we calculate the peak value of the turbulent flow production from the Reynolds stress, that's what's shown on the left-hand side. This is now motivated by some theoretical considerations that came from Pat. This parameter down below is called the adiabatic parameter. It's telling you it's basically a normalized rate of electron dissipation or inverse electron dissipation. So a high value of this parameter means very few collisions as the electrons move along the field line. And a value less than 1 means the electrons are making a lot of collisions as they move along the field line. And this is a key parameter that comes out of drift wave theory. And it sets the phase shift between density and potential fluctuations. And what, following Pat's suggestion from theory, what we see is that the turbulent production rate is sort of, as we raise the density, this parameter is decreasing. So you're sort of moving to the left in this plot. And so the rate of shear flow production drops gradually, and then you get to sort of around unity-ish, something like that, and then it just falls off a cliff. And on the right-hand side, we're showing the turbulent particle flux. That is the rate of mixing, turbulent mixing, carrying plasma from the core out towards the edge due to just turbulent convection. And what you see is a marked uptake or increase in that quantity as the density is increasing, as the collisionality is increasing. If you look at a couple other statistics of this, as well as this work that was done by another student at SWIP, who worked with me about a year ago, looking at the evolution of the skewness in the conditionally averaged events as we raise the density. And the bottom line is, as we raise the density, the skewness out here in the open field line region goes up markedly. That has been known for a long time. And then inside the last close flux surface, the skewness begins to fall. It's positive initially, and eventually at high, as we get very close to the disruption limit, now you actually have negative skewness. That is, you have a negative, on average, a negative density event that I imagine would be going inward radially, although we haven't measured the rate of propagation. On the right-hand side is we can do an analysis called, we can conditionally average these structures. So you set a threshold for quote unquote an event. So typically that threshold is set, and frankly, this is an arbitrary choice, like 1 to 2 times larger than the mean squared deviation of the fluctuation amplitude. So you're looking for quote unquote large amplitude events. And then you go through your time series and you pick out the events, and then you average all those events together relative to the peak event time. And you get sort of an average snapshot of what a large amplitude turbulent event looks like. And then you can do that at different radial locations. That's what these different data, different curves are in each of these different figures. And then you can also look at how that varies as you change the line average density. You can choose both positive going events and negative going events. And so what you see is that at very low density, you don't have a whole lot of large amplitude events. They're rare, no matter where you're looking in the plasma. As you raise the density towards the density limit, you begin to see quite significant magnitude event. These are also offset from each other, just for clarity's sake. You can imagine these are out here, these would all be aligned. So at high density, at the last close flux surface and a little bit inside, you get a lot of large amplitude positive going events, and you also see generation of significant amplitude negative going events around the edge of the plasma. And you don't observe those. We don't have any data for these out in the scrape off layer because there simply aren't any negative going events out in the scrape off layer. And so the intermittency is evolving as you raise the density as well, and as the shear layer is collapsing. This is also just a calculation from the experimental data. Use the measured density and temperature to calculate this adiabatic parameters. That's what's shown on the right-hand side. So the dissipation rate just explodes as we raise the density. Basically going from high alpha, which means little dissipation, to a small value of alpha at high density, which means a lot of dissipation. And interestingly, the density potential cross phase also gets much more pronounced as we raise the density. And that is a fingerprint, a signature, if you will, of a change in the collisionality or the dissipation of the fluctuations. These results of a collapse of the shear layer, a reduction of the nonlinear energy transfer between the turbulence and the shear flow, is reminiscent of results that came out a few years ago. I forgot to put the year in this. Schmidt and Peter in PRL a few years ago from the TJK Heliotron experiment. They did a beautiful set of colloidally resolved measurements of spectral transfer into zonal flow, and they, in terms of dimensional or normalized version of that spectral transfer rate, you see that as you increase the plasma density, there's a marked, almost order of magnitude drop in that energy transfer, reminiscent of what we saw in HL2A. So a sort of a cartoon, a picture that emerges out of these observations is that as you raise the plasma density, the line average density, simply by increasing the fueling rate in the plasma, the collisionality of the plasma increases such that plasma becomes much more dissipational. That also tends to increase the damping on the shear flow or the zonal flow. As a result, that allows the turbulence to become stronger. That increases both, I didn't show it in this talk, but we also see an increase in the turbulent heat flux escaping the plasma. and an increase in the particle flux as well. The increase in transport will cause the edge to cool. Eventually, if the temperature profile gets sufficiently adverse, the change in the plasma resistivity will cause current profile to become eventually unstable, and that will trigger first tearing modes. Those will grow to large amplitude. Ions will begin to overlap. The short circuit, the magnetic confinement, and you get a disruption. But the key thing is the edge cooling is the result, not the cause. The cause in this picture is the turbulent shear flow physics. All right, in the title of this talk, I spoke a little bit about operational limits. And in the last few minutes, let me speak to that. So there's been some very recent work in JText that Pat and some of the students from SWIP have carried out, showing a similar picture that as the density approaches the density limit, the edge profiles evolve, so the edge density gradient increases, grad TE decreases, the shear layer weakens, the turbulent intermittency increases, the Reynolds stress, the Reynolds work decrease. And interestingly, they did some novel new analysis showing that this allows the turbulence to sort of spread more effectively into the scrape-off layer, providing some hints for maybe how to spread out heat flux on the diverter, but that's a whole separate issue. And they argued that the parallel electron dissipation is the key parameter at play as well. So it seems that the turbulent shear layer interactions are key to, because of time, I skipped the discussion of LH transition, but they certainly play a key role in LH transition. They also seem to play a key role in the density limit. And this is reminiscent of both some recently published theory that Jar and Pat, one of Pat's students, published a couple of years ago, and it's reminiscent of some of the computational results that have come out quite recently as well. And you don't have to, the classic way or the older way of explaining the density limit in H mode, a la Drake and Rogers, going back about 25 years or so, is that invoking different linear instabilities in different regimes. So the plasma moves from collisional drift waves in L mode to resistive ballooning modes as you go to the density limit, and E cross B shear flow quenches the drift waves in H mode. But it's you can sort of maybe explain these important operational limits without having to invoke different kinds of instabilities to explain it. It's basically the same phenomena is responsible for all of them. And if that's true, and that's still to be shown, there's that picture then points to an interesting possibility that life might look different when we have burning plasmas where the fusion energy gain is much larger than 1, so that the total heat flux to the system is increased markedly. And I want to just point to, this is maybe an advertisement for, I don't know if you're talking about this tomorrow, Pat, or not. This is the Curry bias. So Pat and his students working on JText, this is like a Back to the Future experiment where they went back to the late 80s, where you stick a small biased electrode into the core plasma to drive a radioelectric field at the last closed flux surface. This is what I spent much of my wasted youth as a PhD student studying in doing what's called biased H mode experiments. In these experiments, they're not trying to induce confinement transition. They're trying to look at the effect that forcing or sustaining the radioelectric field by effectively momentum input from a Lorentz force, what effect does that have on the density limit? So this show a couple slides from their recent paper. Upper plots are showing the floating potential versus radius for 3 different densities. Green is high density, red is low density. Obviously, the radioelectric field collapses when you go to high density in the case where the electrode is not biased. It's just sitting there floating. There's no radio current force, so there's no driving of the shear flow. On the right-hand side is the same data, but now with a strong positive bias. So now you've pulled the plasma, the floating potential of the probe strongly positive, so you get this slope here, so you get a strong positive radioelectric field, even at very high density. And then they reported the result that has on fluctuations and on the Reynolds stress. Bottom line is, with no biasing, as you go to high density, the Reynolds stress gets smaller. Therefore, the Reynolds work is essentially zero. And in the case of strong biasing, you can sustain the strong Reynolds stress and strong Reynolds work, even at approaching the conventional density limit. And then finally, they showed this is the maximum achievable density before the beginning onset of MHD activity, which is the signal for the beginning of a disruption. And on the left is the line average density, basically just average through the central core of the plasma. And that maximum density with positive bias is it's a modest effect, 10 or so, 8% increase, something like that. But at the edge plasma, there's a very marked effect in the maximum achievable edge density prior to the onset of MHD instability when you sustain the shear flow. So why do I argue that this has important implications for burning plasmas? Well, we know that at least in H mode, the strong ion pressure gradient is what sustains the electric field against dissipation. The Reynolds stress is thought to sort of kick the system into H mode, but then if the turbulence is quenched, there's no Reynolds drive anymore. So the thing that sustains the electric field is the equilibrium. So, all right, so if that ion heat flux and the resulting ion pressure gradient sustains the mean E cross B shear in H mode, if we move into, say, a capital Q, the energy gain of a fusion system of order 10 or 20, something like that. Instead of 20 or 30 megawatts of heating in a large tokamak, now you'll have an order of magnitude or more heat flux flowing through the system. And some fraction of that will flow through the ion channel. Most of the energy from the alphas is dumped into the electrons, but all right, some of it will go into the ions eventually. And so I would argue that this may result in a similar increase in the maximum achievable density, not at least reminiscent just to the biasing experiment that was done with JTEX. This also might open the other doors to increase the density limit. If we somehow apply a torque to the edge plasma, I don't really know how to do that, but maybe some clever person will figure it out. Maybe you can engineer the orbit loss of the plasma to help make that happen. And separate from these sort of practical operational implications, this also suggests a causality experiment that somebody should try, namely where you very gradually approach the density limit by ramping the fueling in time, and you very carefully observe the evolution of the turbulence, the edge E cross B shear layer, and the MHD activity in the plasma. And if this picture that we're just presenting here is correct, you should see the MHD activity occur after the onset of changes in the transport. So I presume a transport analysis would show that the evolution of the profiles was because the turbulence changed first. To my knowledge, that hasn't been done yet, but it's an experiment crying out to be done. And so I would point out that there are several papers in the literature now that are suggesting a power dependence for the density limit. This is the Zanka and others. And then very recently, just in the last month or so, a paper by Singh and Diamond came out with basically extending the Kim-Diamond reduced model to now the problem of the density limit, and arguing that in both cases, the dependence is weak. There's some, scales to ion heating channel to some power A, where A is somewhere between a third and a half or something like that. But it's not zero. With that, I'll stop. Thank you.
Very nice results. I hadn't seen the results you showed in the middle yet. The details.
Mhm. Yeah, that came out, I don't know, 6 months ago, something like that.
I mean, there's quite a bit of evidence from earlier experiments that especially Q equals 2 and Q equals 3 drive localized flows, and that also
Yeah.
comes out of global
Yep.
geographies that one was did amongst
Yep.
others and things like that. I would argue that it's not quite, I mean, it's self-organized, all right, but it's not quite the same than something that what we saw about the salinity, for example, that comes out of a system that doesn't have nodes in the sense that condensation occurs because of changes in the Q profile.
Mhm.
So the question is, do we have any experimental evidence for staircases that is not tied to the Q profile? I think that's actually some work from Super, we don't see, we have done the exact same, all of the analysis, and the correlation to Q profile or to low order rational Qs is clearly not straightforward. Yeah. So we would not argue that it's a
From this experiment, we did not do a Q scan or a current scan,
Right.
so I can't say one way or the
I
other.
mean, the other thing that happens when you go to high Q is that the electron transport becomes much faster, right? So that goes a little bit against having solar closely localized solar flows that constrain the radial eddy dimension
Mhm.
and the transport. So from the scaling, at least for the electrons, goes in the other direction.
Yeah, no, those are all good points, but the data that we have pretty clearly show there's a coincidence between these sort of weak corrugations, modulation of the radial correlation length, a flip in the propagation direction, change in eddy tilting. It's like, oh,
So
sort
that
of
was very clear.
if it looks like a duck and quacks like a duck.
That was very clear.
Yeah. But it would be very useful to try that across, do a systematic parametric study. How does Q profile change with this? As you change the heating, as you change plasma shape and so on. None of that has been done. Could be done on D3D.
It's a little bit difficult because, then of course, with
To reconfigure the BES array. Yeah.
Even the BES, the longer.
I talked to Zhang and she said that they could do it. So it's not in the program at D3D. So. Yeah.
Mentioned at the beginning of the talk that pellet injection actually
Yeah, this is the old Greenwald results. Yeah.
So who does it fit exactly? Is it just the fact that for given average density and lower, or is it?
I think so. That's my naive interpretation.
The change of the density gradient change the stability.
Yeah. Yeah. But I mean, I think to try to unravel that again,
The pellet,
you need to do the pellet experiment and do these kinds of measurements.
the pellet doesn't really beat the density. Structure. Right? What happened in that ancient history was we shot in the pellet, and they have an adiabatic relaxation that as opposed to puffing away on the gas, cooling the edge, and breathing gas. So the argument, the point of Greenwald was that was evidence to support there's more going on in the density. This, I think, is just a stupidity that has propagated for 30 some odd years to equate Greenwald's point is that if you still, the system will enforce a density limit by transport without any disruption. in the other thing that's in these recent things from JPEX is that there were some of these cases that he showed, you're able to, you don't beat with the bias, you don't beat the line average density limit that much, so 10% effect.
Yeah, the edge is.
Double the edge there. Look at the picture. Look at the red, right? So you're getting basically a 10% effect in the line average, but look at the edge density.
And I don't think this was ever published, but I remember going back again to my friend in Bob Taylor's lab, you remember. If we ran high density bias H mode experiments and then you close to the density limit, Bob didn't like to use the green wall limit. That was his favorite scaling. But anyway, if you ran close to where you could safely operate in the absence of H mode, when you turn on the H mode, the density would actually climb higher. And then if you turned off the H mode in the middle of that, bang, times would almost instantly disrupt. So if the edge was above its sort of desired limit, and then also it lost the Lorentz force drive for the cosmic shear flow of the boundary. So,
but you also change the source, right? So
yeah.
And then through the electrical processes, you can release a lot of filters.
Yeah, and I mean, this is why I think the causality experiment would be where you slowly ramp and you watch the whole system evolve at the same time. And then you have to do a very careful transport analysis of an evolving discharge. Would probably give us a pretty clear indication that in fact this is the case.
I can give you a sneak preview of this results from
Okay.
These bias things, and then do a slow ramp down of the bias.
Mm.
You understand? The system will disrupt before you ramp the bias all the way off. So that I think is simple causality demonstration. You're above the, you're above the initial density limit. You start ramping down the bias to weaken the shear layer, and you disrupt before you go all the way down on the bias. And the other thing that's interesting in all this is there's this stupid religion about this subject of the correlation of this parameter alpha, the elasticity with the behavior. But one of the things that's published already, you don't have that. You have that picture, the thing of the ramp up and down of the bias.
No.
It's in that paper.
Yes, not in these slides.
Figure 13
Yeah.
of that paper.
Yeah.
One of the things.
The hysteresis curve.
Yeah, you get a hysteresis. We made a plot of alpha versus the bias. See what I mean? And you go up and down and you get a hysteresis loop. What a surprise. And the alpha is clearly following the bias. The shear layer seems to be the fundamental thing, not the alpha. The alpha goes along for the ride. That's something we want to do more experiments on.
And I guess I would also argue this is not just of academic interest, because operation and high density is key for future plans and so on. So.
Since we're here, I can just sneak in a comment. I don't know if it's for you or for that, but how about the density limit in high node? Because some of that has features of nodes. So do you know of experimental data on that?
Peter, do you know of anything in I mode? What did you said something, Lothar?
Or you go into H mode.
Are you going to the edge mode?
You have to put power in your H mode.
This is not the point, what I would have. So the edge mode, you're not going to stop. So you will not go.
Well, you fall out of H mode back into L mode first, and
That depends. If you are in low density, then you have L mode.
Yeah.
High density, then you have L mode. If you keep it in
power. Finally, you might think they get more shear and more radiant, more better. The problem is if you get the ballooning movement, then this is break your density.
Yeah.
The ballooning movement is by fraction more. Therefore, you have this effect. You cannot do something against the ballooning pressure position. So you can put as much power as you want to, you would not overcome the.
Yeah, no, I would agree that I wasn't trying to argue that, oh, we'll be able to go to, 5 times the normal operating limit. Something else is going to limit the operation, probably some sort of MHD stability limit.
Yeah. So I find it really interesting that your pressure density gradient HFA experiment.
Yeah,
It's possibly near detected rock, but I have sometimes the same impressions of it.
Frankly, was surprising to me. I expected the electric pressure gradient to be weaker as we raise the density.
Yeah, I
But
also would expect.
if I just naively take the temperature and the density we infer from the probe, multiply it together,
So for example,
Makes
also
sense.
with Giacomo-Ricci technology, obvious makes also completely sense, and if you increase the density, the gradient will get better because you might think that the first confinement,
Yeah.
the gradients of the different would make sense.
Yeah.
Do you have an idea why it's deeper?
do I?
Yeah.
No.
But do you know someone else who might have an idea?
No, I always thought that was a puzzle.
This is the most fascinating thing. So it doesn't really get clear. But it is experimental measurements and effect.
Or the measurements screwed up somehow. Yeah.
The density is the lowest. So the most correct. ET is from the lowest power.
Yeah.
Switch to the
Yeah, I wanted to go on the density. So, I mean, one of the things, I want to point out, the Zanka paper is a fit to a bunch of
Yes.
plot points.
It's not a theory.
Well, theory has its problems too, but there is some physics in it. I mean, in the thing we did was based on working with the coupled equations for the zonal flow, the fluctuations, density, and temperature.
Yeah.
Okay. Now, one of the things, by the way, it's important to say that all that was done below the LH transition,
Mhm.
right? Which is definitely in that system of equations. It's the Tynan model, basically extended, right? So that's a power scaling in Elmo. Very important point. One other little bit of advertisement is that there's an interesting hysteresis phenomena in that, which is not the usual hysteresis, because of course there's no stability. It comes from the time variation, and there's a signature of that effect that goes beyond the scaling law, which I think that's testable, and I think some interest. But the point I wanted to drive at, it seemed to us when we were playing with that system that you really now can have almost a triple point between what I might call the L mode, the H mode, and now the density limit regime. Okay, in other words, if you think of it, this problem really has 3 phases. And the conventional wisdom is you must pass
From
through
L
L
to
mode,
H.
but I mean, in these high power regimes.
It may
which-
not be a bifurcation.
Well, it could be different. And you have any thoughts on that?
No, I mean, I understand the argument, but I don't know of any experiments that.
In hydrogen that is usually deteriorated or degraded pedestal, sometimes the density doesn't really increase anymore. When you have high density already, you try to make an H loop, you get a little bit, little steepening in the gradient, but it's sort of the density is already so high that it's close to the pedestal.
Yeah.
Not necessarily the line average density limit, but the pedestal. And then sort of not much difference between that and H mobility.
Well, that would be kind of back to Pat's point. So now we have like a supercritical plasma state.
Well, I mean, I think it's an interesting question that could be tested down the road.
What we see in the simulation is that the paramagnetic component of the Reynolds stress, which is the relation between the flat waves of the radial component of the paramagnetic grid on one hand and the radial component. So that's part of the Reynolds stress, which is not looked at usually.
In any extent, it's not.
So, well, what we see is that it's phase and it's kind of twice the magnitude of the
The electrostatic component. It's larger than the electrostatic component.
exactly. Okay. I was wondering whether you might have a way to measure this, because I guess that with the magnetope that might be visible, at least the density part of the dynamic.
Is this an ion dynamic?
Yes.
Not with probes. It's when Lotar does the velocimetry that Zeng does with BES capture this, do you think? Or
You mean
I don't know if you heard the question.
I think the diamond rating is always part of it, right? I mean, because there's also a screening effect. You see that in the simulations also that basically the diamond ratings adjust once the flow is there. Ratings adjust so that it's sort of the zonal density.
Why can't you measure the density part? If you know the ion temperature, why can't you measure the, you'd be looking at a cross correlation of V with something, another
just-
gradient event or something?
But you're not measuring the 3 probes or the 4 probes that was measuring. Usually, some are trying to measure space potential, but usually it's floating potential. Can't measure the density of the floating potential. Other set of probes. I guess principle you can have a density fluctuation, and you have to know the ion temperature. Neglecting ion temperature fluctuations, I don't know if those are important or not. So you get a part of the ion pressure.
You cannot get it in performance plasmas. You can only get it in low power only plasma. I mean, inside the plasma flux.
At least in the laboratory plasma device, the ion temperature is 10% of the electrons.
Yeah, also, it turns out true that this is an important player in the then this component might depend maybe more critically than the electric one on the extremity drive. Because then the pressure equation plays a role, and whether it's gateway or ITG or something else.
Peter, do you want to respond?
Yeah, I think sort of difficult to find temperature.
Yeah. See,
You don't have a lot of points, a lot of more points to try to keep it. We essentially have to come up with a not indirect way of
Is there experimental observable steel of phrase from biomechanics?
If you believe the story, there should be, if you could pin down a difference in the mode, there might be, right? Between drift wave and ITG.
This is the first time I've heard such a suggestion. I have no idea how we would measure it.
You might probably see a difference scanning the fusion. That's directly, in our case, it comes from FLR effects. So it's scanning the heat with different pressure fluctuations. So with the scanning the heat, cost component between peak tilt.
Has a different growth star scale.
Well, I think the most of scaling from the peak tilt fluctuation. Well, that would be only the density from the sun. You should not be able to measure the temperature.
Not a fluctuation.
The density would be approximate.
In the case of interest, probably
Okay.
PI equivalent counts.
So you're arguing it's the difference in the relative contribution of the stress versus magnetic stress.
The red walls.
And also this whole business about magnetic stresses.
Assuming specific.
I'm sorry, I have to, the air conditioner makes it hard to hear.
Yeah, at some point you show that the creation of tension is always involved where you are positioning the edge.
Could you say it again? I didn't follow.
Sorry, the potential fluctuations are lower in the core when you have shear layer at the edge.
In the laboratory classes,
Yes.
yeah.
Yeah. You also mentioned that the turbulent structure and the radially extended state computation are also bigger in that region.
I've seen the coconut long range laboratory scale.
I think
I mean, the laboratory scale plasma, most of the intuition I think that we have developed about the turbulent shear layer interactions is assuming that like the boundaries are infinitely far away. So scale separation between the size of the system, the gradient scale lengths, turbulent formation length, and the shear layers. So the laboratory device, that's all out the window. They're all roughly the factors of 2 and the same. Plasma is 5 centimeters, shear layer is about 2 centimeters across. ROS is 1.5%. There's no, so it's really like a system. That's the only hand waving explanation of the observation. Essentially, the center of plasma knows what's going on at the edge. And they're tightly coupled together.
we are the laboratory. I think you observe the sensitivity coming of the waveform.
Oh, yeah. So if you're just above the onset of the drift waves, there's a very narrow window where you can actually get like one eigenvalue, like a nice sinusoidal oscillation. But as that amplitude gets larger, then the drift wave itself will modulate locally the density gradient as you go around that. So there'll be the total instantaneous gradient will have regions where it's slightly steeper, slightly shallower. And the phase velocity of the drift wave and the downward gradient. Because this is my hand waving explanation. So what that leads to is wave steepening. And if you look at, if you Fourier transform that, what you get is Fourier series of a triangle wave, you get a series of lines. And that's exactly what the spectrum looks like. And then when that steepening gets sort of the wave could break, so that it was sort of, we now have basically a bipolar value of density, then that's when the onset of no longer coherent activity. So that's basically wave breaking. the steepening is caused by the fluctuation self-modulates the background drive of the fluctuation. It's the beginning effect of a nonlinear wave.
You're on.
Okay.
More questions? Well, let's thank George again.